All right, so we'll talk about capacitors today. Okay, and their so capacitance is their capacity to store energy. Okay, so let me show you. Let's start off by showing you how a capacitor works. Did you?
I think I saw it up higher. Keep going. Second or middle row, capacity level, capacitor level.
Yeah, bottom,
Yeah, bottom now.
No, there. All right. So here's a circuit. Okay, so here's a battery. Here's a capacitor. This is called a parallel plate capacitor, and then this is just a light bulb. All right. So what we're going to do is okay. So what we did was what happened was, and this happens really fast. So what happened was electrons flowed from here to this metal, this conductor, and these electrons repelled the electrons here, and those electrons got to the battery. So this capacitor is charged now. Okay, so this is uncharged, and we charged the capacitor. Okay. Now, what we have done is, and you can see that this is these charges want to attract each other. So if you're holding them apart, it's like you've stretched a spring. Okay, so you have stored energy in a capacitor when you've charged it. Okay. So what did you do? You moved energy from here to there. Why would you do that?
So you can use it.
Well, why not use it directly from here?
it can discharge much quicker than that.
Yeah, so this thing can discharge much quicker. This thing will release its energy much quicker. How quick? Well, you can control how quick it'll do that. From anywhere from milliseconds to nanoseconds. Okay, and the way you control that is the resistor through which it discharges. The smaller the resistor, the faster it'll discharge. You know? So let's discharge this. Now you discharge it to that through that load. Okay. So you can discharge this capacitor as fast as you want. Okay. What is the price you pay? The faster you discharge, what happens?
There is more heat generated.
There's a larger current. Okay, and things might burn and stuff like that. Okay, so you will see applications where we'll look at fusion reactors, where they shoot laser beams at a pellet and try and get a fusion reaction going. And this is a national high at Livermore and all those places. They discharge these capacitors in microseconds to nanoseconds. Okay. All right, what do you need to make a capacitor?
Two metallic plates.
Any two pieces of metal. It can be anything. Two cups, metal cups. You can take a faucet and anything. Okay. Now this is a common configuration. This is called a parallel plate capacitor, and this we typically use this because we can give you the capacitance in terms of its geometry. Okay, so we can give you a formula for that. All right, so again, we use capacitors because we can store energy and discharge that energy as fast as we want. Okay. So this actually is a fairly common circuit. Okay, so we've charged this capacitor. This could be a flash bulb that you use in your camera, okay? But this could be somebody's heart that is chaotically beating, and you can defibrillate it by passing it, giving the heart a jolt, okay? So there are several applications of this simple circuit. Okay, so let's so that's the subject we're studying, capacitance. So we'll look at energy stored in a charged capacitor, and so on. Okay. Capacitors are used to tune receivers. Okay. So in every tuning circuit, so do you guys use a tuning circuit?
I don't know what that is.
Okay, here it is. So you haven't learned about inductors yet, which you'll learn next a couple of chapters down. Okay, so here is an antenna. There's a capacitor, and there's the inductor. The inductance is L, C. You know resonance? What is resonance?
It's the natural frequency.
Yeah, so the frequency at which this fella oscillates, so if you excite a system at its natural frequency, if you drive a system at its natural frequency, then you can set up large amplitude oscillations. Okay? The natural frequency of this device is that. Well, so what? It's a big deal. All right, so here's the deal. So let's when you tune into a radio station, how does that happen? Okay, so right now there's how many FM signals are there in this room?
Hundreds.
Hundreds. How do you pick out the ones that you want to listen to?
I think classically you'd have a mechanical wheel that changes, I guess, what are you touching on the inductor?
Yeah, you're either changing an inductor or a capacitance. So what you're doing is, so let's say you want to pick up 89.9 megahertz. Okay. What you do is, well, there's 101 signals here, F1, F2, F3, and so on. And so when you want to pick up this, what you do is you change the capacitance or the inductance such that its natural frequency becomes that, and now that frequency will excite the largest current in there, and that's what you pick up. All these other guys will not drive as much of a current. You guys remember when you were vibrating the string at different frequencies other than the natural frequency, it didn't vibrate with a large amplitude. Only when the frequency matched the natural frequency, you set up large amplitude oscillations. Just like that. When the frequency matches the natural frequency, you set up large amplitude currents in you. So here's a capacitor, and this is a tuning circuit. And where do you have them? Every wireless device has it. So there's trillions and trillions of these circuits in the world. At the heart of every wireless device is this circuit. And so that's what that is. As filters and power supplies and energy and charge storing devices, and we'll look at an application for this later. Okay? So capacitors store electrical energy just like batteries. How fast does your battery release the energy? Slowly. The fastest you can do is a couple of 3 hours and stuff. Yeah. And you can release that energy stored in a capacitor extremely fast. Okay. So the capacitors can discharge the energy much faster. So here are some numbers. Energy stored in a capacitor is used to light flash bulbs. Okay, so 20 joules What can you do with 20 joules? 1 kg, 0.2 meters. Okay, so m g h. Okay, so 2.5 pounds, 2.5 pounds dropped from a feet to the ground. That's how much energy 20 joules is. Okay, so that's how much energy you store in your capacitor when you take a flash picture. Okay. So what does this do? 20 joules is 20 kilowatt for a millisecond. So 20,000 watts times 10 to the minus 3 seconds. The seconds, watts is joules per second. 10 to the minus 3 kills those, and so that's 20 joules. And so what does this do? It's 200 into 100 watts into 10 to the minus 3 seconds. So here's what that flash bulb did for you. It lit up 200 100-watt bulbs for a millisecond. That's what 20 joules did for you. Okay, 2 pounds at a height of 1 feet. That's what it did. Why did you do that? So you could turn total night, complete darkness into daylight, take your picture in a millisecond, and then it can be night again. Yeah. All right, so to make a capacitor, all you need is 2 hunks of metal. Yep. And to charge a capacitor, all you do is connect it to a battery. What happens? Electrons flow from here to there. These electrons, this negatively charged metal repels electrons, and these electrons flow here. And this thing is charged now.
How do you know which side loses electrons?
I'm sorry?
How do you know which piece of metal loses electrons?
So this is the negative terminal of the battery, and electrons move. Yeah. So any 2 conductors can make a capacitor. Okay. So when you charge the capacitor, you move energy from here to there. The capacitance of a capacitor is how much charge it can hold per volt. Okay? The more charge it can hold per volt, the greater the capacitance. Okay? So and capacitance is measured in the units for capacitance are farads, in honor of Mr. Farad. Okay? And 1 farad is 1 coulomb per volt. A coulomb is a large charge. A thundercloud will have 10 to 50 coulombs of charge. So most in a lot of your circuits you use microfarad to picofarad. That's 10 to the minus 6. That's 10 to the minus 12. Okay. Here's the electrical symbol for a capacitor. This is the electrical symbol for a resistor. Here's the inductor, which you'll learn about in a couple of chapters. You will learn that, so when you charge a capacitor, you see it's creating an electric field. A charged capacitor has an electric field. So you can think of the energy stored in the electrical field. Okay? So anytime you create an electrical field, you've stored energy there. Okay? An inductor stores energy in a magnetic field. So when currents pass through an inductor, in a solenoid, you have magnetic fields inside the solenoid. Okay. So we'll learn about that. Here's a switch. Here's a battery. There's the negative terminal of the battery. Here's an AC source we'll learn about. An ammeter. What is an ammeter? Do?
Measures current.
Measures current. A voltmeter measures voltage. Galvanometer. It also measures current, but it's an old time. Yep. Okay, so charging a capacitor, you saw we charge the capacitor. Here is a here's a battery. When you close the switch, electrons flow like that, and these electrons come back to the battery like this, and the capacitor is charged. And then it's ready to use. So when you take a flash picture, when you close the switch, that's when that amber light is blinking, when the capacitor is charging. And when the capacitor is charged, that light goes green, the switch opens, and you're ready to take a picture. Okay. And then when you click your camera, you close this switch, and the capacitor discharges through the flash bulb. All right. Okay, so when you're charging the capacitor, charges flow from here to there, and then electrons flow back to the battery. Well, how much charge flows in the capacitor?
Well, nothing flows through it.
Yeah.
It's just from one, it's the difference in charge across the plates induces flow until it is fully charged.
Yeah, when is it fully charged?
It's proportional to the voltage applied.
Yeah, so when the voltage across this equals the voltage of the battery, that's, okay, so, and that's when the charge flow stops, okay? So charges flow into the capacitor plates till the potential difference equals the terminal voltage of the battery, okay? So electric field at this point in the wires goes to zero, okay? And that stops the flow of charges. So here's a parallel plate capacitor. Okay, you can take two metal plates and hold them parallel to each other. So you can take two aluminum sheets and make a capacitor. And the capacitance is given by, so this is air filled, okay, epsilon naught, which is the permittivity of free space, times the area of the plates divided by the distance between the plates. Okay, you will see that you will want larger and larger capacitors when you want to store more and more energy. So what can you do to make a capacitance large? So you can make the areas of the plate large or decrease the distance between the plates. Okay, or do both. Now, of course, making the area large can be inconvenient. You don't want to be carrying large objects around. So we'll see how to increase area. There are things called supercapacitors. Okay, back 20, 30 years ago, a 1 farad capacitor was quite large. Now you can buy on Amazon a 5,000 farad capacitor for less than $100. So. All right, so there's the capacitance. Now, let's say I charge this. What do the charges want to do? They want to attract each other. So what is preventing that? Right now it's air filled.
Whatever is connecting them to the battery itself.
So, yeah. So you have to have, the easiest thing to do is fill it with a dielectric, insulating, let's say a piece of plastic or whatever. Okay. So it gives mechanical support to the thing, or you can do the following. So here's an aluminum sheet, here's a paper sheet, here's an aluminum sheet. Okay. So that paper gives you mechanical support. In addition, it increases the capacitance of the capacitor. Okay, so we'll talk about something called a dielectric constant. And if the dielectric constant is 5, it increases the capacitance by 5. Okay. So dielectric constant, we'll talk about that. Is kappa. Here's a cylindrical capacitor. A coaxial cable has a capacitance. Okay. Right. So remember, to make a capacitor, all you need is two pieces of metal. So here's Here's the central wire and there's the surrounding wire, okay? And the capacitance for length L for this configuration is, now we are showing capacitors where we can give you the capacitance in terms of the geometry. That's what we're showing you, okay? You take two pieces of metal, I can't give you a formula for the capacitance, okay? So I'm giving you capacitance for a regular geometry, okay? And by the way, when you charge a capacitor, so let's go back. So you see the charge resides on this surface, on the inner surfaces, and here. Remember, charge resides on, when you put charge on a metal, where does it reside? On the surface, okay? And so the charge is only on this surface and this surface. Okay? So for this guy, the charge will reside on this surface, inner surface, and the outer surface there. For a cylindrical geometry, the charge resides on the outer surface of the inner conductor, and the inner walls of the outer conductor. So here's the capacitance for length L, log of B over A. Yeah. Here's two concentric spheres. Okay, so there's the capacitance of this guy is AB. A is the radius of the inner sphere, B is the radius of the outer sphere, divided by Ke, the Coulomb's constant, minus B minus A. Okay, now what you can do is make the radius of this guy go to infinity. So you're really making a capacitance just out of a single sphere. And the capacitance of a sphere, of a metallic sphere, is A over Ke. Okay. So, and that's what you see. You guys might have seen, what do you call those things? The name is escaping me right now. Anyway, you know, you've seen a metal sphere and then sparks flying off. Yeah, Tesla coil. Yep. Yeah. So the capacitance of that object is 4 pi epsilon naught times A. Yep. So let's say you want $37. How do you get $37? Does the government print a $37 bill? No.
You have 37 $1 bills.
Yeah, so there's various combinations, right? So just like that, we do that with capacitors as well. Okay, you can combine them. So if you want larger capacitance, you just connect them in parallel. Okay, so when you connect them in parallel, the effective capacitance is just the sum of these two capacitors. Okay. And so when you'll learn in this one example, you have a whole bunch of capacitors connected in parallel. Each of them stores energy, and they're all fired at the same time. They discharge their energy through a laser, which is shot at a pellet to have fusion reaction. Okay, so when you want a larger capacitor, you connect what you have in parallel. Okay. Now, all these guys are connected to the same battery, so they all charge to the same voltage, the voltage of the battery. Okay. When you connect them in series, the effective capacitance is smaller than the smallest one. Okay. So when you want a smaller capacitor, you connect them in series. Now when you connect them in series, okay, so let's watch this. Electrons flow from here to there. then what happens? Let's say if 10 electrons flow from here to there.
And then 10 protons will be on the opposite plate.
Yeah, they reflect 10 electrons. So these 10 electrons move over here. These 10 electrons reflect these guys, 10 electrons move over here. So when you connect a bunch of capacitors in series, they all charge to the same amount. The charge on all of them are equal. Okay. Okay, so the charges are equal. The sum of the voltages is equal to the voltage of the battery. Okay. The equivalent capacitance is given by the inverse sum. And you see, notice this. See, this is positive, this is positive, this is positive. So this is the biggest number because it's the sum of these numbers. So this has to be the smallest number. Did you guys understand? Okay. So when you connect capacitors in series, the effective capacitance is smaller than the smallest one. You'll be solving circuits eventually. You'll have a mess of capacitors like this. And eventually you'll need to find what is the charge on each one of them and so on and so forth. So what you have to do is, you have to do it backwards. You have to reduce this to a single capacitor first, find the charge on that, and then work backwards. Okay, again, I'm talking about in the future. Okay. So right now we'll show you how to reduce this capacitance, this mess of capacitance into a single capacitor. So these are the two rules we'll use, series combination and parallel combination. Okay. So when you have a mess like this, see these two are in parallel, so you can reduce that to a single capacitance. When they're in parallel, you just add them. So 3 plus 1 is 4. 6 plus 2 is 8. And now these two guys are in series. These two guys are in series. And you add the series combination, you see these two combined is 2 units. These two combined is 4 units. And now these guys are in parallel and you just add them. So that's how you reduce that to a single capacitor. Okay, when you store energy in something, see when I lifted a cup, I did work on it. And by doing work on it, I transferred energy from me to this thing. Let's say you're charging a capacitor. As you're charging a capacitor, see this had negative charges, and let's say it had 10 units of negative charge, and you're pushing more negative charge on that. So to charge the capacitor, you're having to do work, right? I mean, there's negative charges sitting there, and you want to put more negative charges. You got to push this charge in there. Okay, so when you're charging a capacitor, you're doing work to charge the capacitor. And every time you do work, work is a mechanism of transferring energy from one object to another. So when a capacitor is being charged, the battery is doing work. And when the battery is doing work, it's transferring energy from the battery to the capacitor. Okay? Just like when I lifted this cup, I did work on this cup and I transferred energy from me to the cup. All right. So, work must be done by an external agent such as a battery to charge a capacitor. This energy is stored in the capacitor. And here's how much energy is stored in the capacitor. 1/2 CV squared. C is the capacitance of the capacitor, and V is the voltage to which you charge it. It's also equal to 1/2 Q times V. Now it can be, when you charge a capacitor, so for an ideal capacitor being, let's say, infinitely large plates and close by, the electrical field will be only between the plates. These fields will be negligible, you know? So when you charge a capacitor, you can think of that the energy stored in the capacitor is in the electric field. Yeah? Because what is the electric field when the capacitor is uncharged?
Zero.
Zero. Yeah? So here's that should be U. The energy stored in the capacitor is 1/2 CV squared. For a parallel plate capacitor, C is that fellow. V, the voltage to which you charge the capacitor, is the electric field times D. And you square that. And so if you rearrange all of this, that's A times D. A is the area of the plate, D is the distance between the plate. And what is that? That's the volume contained in it. Times this. So it seems like this is energy density times the volume gives you the total energy. Okay, so U is the energy density, meaning that's how much energy there is stored in the electric field per unit volume. Okay. So the energy density in any electric field is proportional to the square of the magnitude of the electric field. Okay. So whenever you create an electric field, you've stored energy in the field. You can think of it that way.
When calculating area, are the plates always going to be considered the have the same area?
No, I mean you can make capacitors out of anything. This configuration. When you have this configuration, that's when that formula is valid.
So do you only use the area where they are overlapping?
Oh, no.
Small.
No, the capacitance will depend on this area as well. I just don't have a closed form formula for it. You can make this capacitor too. You can make anything. We don't have a formula for it, that's all. And no matter how the conductors are, the charges will always be equal. So capacitors with dielectrics, remember the air-filled capacitor, they want to attract each other. So the easiest thing to do is put a dielectric in between. A dielectric is just an insulator. So it could be a piece of plastic or whatever. Okay? When you put a dielectric in between, the capacitance increases by a factor called the dielectric constant of the material. Okay? So if you increase the capacitance, with the dielectric present, capacitance increases by a factor called the dielectric constant. Okay? A dielectric is a non-conducting material. Okay. So dielectric constant is denoted by kappa. So in this region, in a region where the dielectric is filled, wherever you have epsilon naught, replace that by K epsilon naught, or just written as epsilon, okay? And you get the corresponding equation. So the electric field in this region becomes 1/4 pi epsilon naught Q over R squared. Okay, so if you had a point charge in this region, the electric field in vacuum is given by 1/4 pi epsilon naught Q over R square. This is the electric field around that. Now, if you have a positive charge inside a piece of plastic, the electric field here is given by 1/4 pi epsilon Q over R square. That's what we're saying. Okay? All right, as far as we are concerned, you put a dielectric in between and you're increasing the capacitance by that factor. Yeah. Okay. So here's a capacitor. When you put a dielectric has molecules with dipole moment, or the dipole moment is induced in this electric field. And what these dipole moments do is they create a field in the opposite direction, reducing the electric field here. So if E is the electric field here, when you put the dielectric with the same charge, the electric field in the dielectric is reduced. Okay? And what that does is, so now, what does electric field do for you? That limits the maximum charge energy you can store in the capacitor. Why does it limit that?
Because it exceeds the 3 times 10 to the 6
Very good.
coulombs
Yeah.
of discharge.
So air is an insulator. It'll break it down and make it conducting. Okay? All materials can be broken down. All insulators can be broken down. You can have lightning in plastic. There. Except that the field strength required is much higher. So you can charge it to a higher voltage. The dielectric strength of plexiglass is about 30 times 10 to the 6 volt per meter. So 10 times stronger. So to make lightning in plexiglass, you need a field 10 times stronger. So that tells you can charge it that much higher, that capacitor, with that plexiglass in between. Okay? So whenever you have dielectrics, the field inside is reduced, and so because of these induced dipole moments in the insulator, and you can charge it to a higher voltage in the presence of an external. This results in the reduction of net electric field within the dipole. So dielectrics have molecules with permanent dipoles, or molecules in which a dipole can be induced. So here's what the dielectrics do. They provide increased capacitance. And that's a good thing, because remember, the energy stored in a capacitor is 1 CV squared. Okay. They provide increased capacitance, and in addition, you can charge the capacitor to higher voltages as well. So you can store much more energy. Okay. Increased maximum operating voltage, and then mechanical support as well. What do we mean by mechanical support?
Prevent them from coming together.
That's right. Yeah. So here is the dielectric strength for various material. What this tells you is, at these electric fields, you'll have lightning in that material. That material will break down. Air, you saw that is 3 times 10 to the 6 volts per meter. How does it break down? How does air break down?
Produces lightning.
Yeah, well, how does that happen?
It accelerates electrons so fast that it knocks electrons off of their...
Very good, very good. So if there is any stray electron milling around in that electric field, that stray electron will get to speeds between collisions where it'll start knocking off other electrons. So that's the dielectric strength of air. For glass, it's about 5 times greater. For Teflon, 20 times greater. Okay. And so on. silicone oil, 5 times greater. You can break down any material, okay? Meaning you can create lightning in any material. So the dielectric strength of plexiglass is 10 times that of air. Right, so here's a way to make a capacitor, large capacitor in a compact form. Conductor, insulator, conductor, insulator. And then you can roll them up. Yep. Here's a capacitor with interweaving plates. Why did you interweave plates? What did you achieve by doing that?
You created a parallel set.
You effectively increase the area.
Oh,
Yeah. And the oil is the dielectric. Yeah.
For B, would you consider those to be in series or parallel?
like you said, it's just one, it's essentially one
Yeah.
place, just a larger area.
Yeah. Mhm.
Okay.
Mm.
No, I got it.
But-
I had the same thought.
I didn't understand the question.
But so here you increase the area, but you can think of this larger areas, 2 smaller or 3 smaller skins in parallel. So you can think of it that way too. Okay. We'll use that trick in a second. All right. I don't know if those keyboards work like this, but here's something you can do. I don't know if keyboards. All right, so how does the computer know which key you hit? So here's one way of knowing it. Okay, so all these guys, every key is connected to 5 volts. Capacitance is Q times divided by V. So this is 5 volts. That's fixed. Okay. Now when you hit this key, D decreases, and the capacitance is epsilon naught A by D. When D decreased, capacitance increased. So when you hit this key, the voltage was the same, capacitance increased, charge flows in there. That's how the computer knows which key you hit. Yeah. So here are some big boy toys. Why are we pursuing fusion reaction?
If it's achieved, we could technically have infinite energy because it could be self-sustaining and it doesn't produce much waste.
What do you mean self-sustaining?
Like the fusions themselves could incite other fusions.
No.
I thought the output of tritium could be used in other fusion reactions. Unless I'm fully misunderstanding what's happening.
Yeah, okay. All right, so we have limited supply of fissile material. So 10,000 years from now, you won't have fission reactors, maybe. Okay. So, but the main problem is the following. So here's uranium-235, and it's nowhere near a problem compared to carbon dioxide in the atmosphere. This stuff is radioactive for 25,000 to 100,000 years. Yep. With fusion, nothing is radioactive. And also, So this is limited supply. This is not limited at all. Why are you getting energy?
The strong force.
Yeah, so these guys are bound, and anytime they're bound, they weigh less, and that missing mass got converted to energy. Yeah. All right, so that's this is what essentially you want to do, okay? And for the strong force to take over, you got to get them real close, okay? And so what you do is you shoot lasers at pellets, heat it, and this pellet heats to a couple of billion degree Kelvin. And a few of those will come close enough and fuse. So these pellets are heated to a couple of billion degree Kelvin in a lab. Do you guys know what is the temperature of the center of the sun?
6,000 Kelvin.
That's the surface temperature. At the center, it's only 15 million Kelvin. So you're heating this pellet to 1,000 times greater temperature. Okay. All right, so the Z machine is a controlled nuclear fusion reactor at San Diego National Lab. It uses a bank of capacitors connected in parallel and stores 1,000,000 joules of energy. How much does your flash camera? 20, so 10 joules. So this is 100,000 times more. The energy is discharged through a target about 1 cc. 1 cc is hold up your eraser. Half of that is about 1 cc. In a few nanoseconds. Okay. And heats it to a temperature of 2 billion degree Kelvin. Okay. The power output of the Z machine is about 100 times the power output of all power plants on Earth for those few nanoseconds when the lasers are firing. And so here's another facility in Lawrence Livermore Lab. And the capacitors are charged over a period of 90 seconds. So you're charging them over a minute and a half and then discharging them in half a milliseconds. So we want to make supercapacitors. Here's to make super. So these buses, at every bus stop, the capacitor gets charged. Okay? And you can charge a capacitor super fast, 20 seconds, 10 seconds. Okay? By the time people get on and off, you charge the capacitor, you can go to the next stop. And not only that, so supercapacitors last 10 to 20 years. Okay? Whereas a lithium-ion battery has only about 5 years. Lead-acid battery, okay, lithium ions can have charged and discharged 500 times. Capacitors can be charged millions of times. So they're indestructible. You just can't store enough energy to go from here to New York. I mean, unless you have a charging station every 10 miles, you know. So they're great for public transport in a city and stuff. Well, the thing is, to store energy, the more energy you want to store, the larger capacitor you want. Okay. Here's for a parallel plate capacitor. Okay. More energy you want to store. the larger the area you want. The closer you get, the sparks will fly. Okay. So a practical way to increase the capacitance is increase the area. And they effectively increase the area by putting charcoal, powdered charcoal. So the surface area of all those particles add up, and that's the area of the plate. Okay. So supercapacitors are made using a material with very large surface area between the capacitor plates. 2 layers of activated charcoal are given opposite charges and separated by an insulating material. So the activated charcoal is your plate. The surface area of all those particles is the area of your plate.
Is activated charcoal considered metal?
Yeah, I guess so.
Actually, what is charcoal? It's just carbon, right?
Okay, charcoal is carbon, yeah. Okay. This produces a capacitor with capacitance millions of times larger. Okay, 5 kilofarad capacitors are commercially available. Okay, price one on Amazon?
Less than 100.
Yeah, no, price it. Get your phone out and
Over
phone.
Amazon?
The potential difference can only be 2 to 3 volts. And you can store about 10 kilojoules of energy. Okay. All right, so